Thank you. I have the advantage of having used this already yesterday. You have the disadvantage of having me up here again for the second time. I promise to speak about something completely different from yesterday to make up for it. Do I need to? Yes. No? Here we are. So I want to speak about something different, which is related to quantum measurement, and in particular, a hypothesis that we've come up with this year on how something called objectivity can emerge from equilibration. And so to get started or to get into this is a familiar point to probably all of you that quantum mechanics, as per the textbooks, per the postulates, recognizes two forms of evolution essentially, right? One of them is the reversible part, the Schrödinger equation, the unitary part, and the other one is quantum measurement, right? And so that's irreversible in principle, logically and dynamically, once you have a model of it. And so what people have been asking since the origin of quantum physics is, do we need that second part? Yeah, if we have the Schrödinger equation, can we derive something that brings this irreversibility, that gets rid of it in a sensible way? Yeah, meaning, can we make a model of quantum measurement without using the measurement postulate? Yeah? And there's a lot of variations on this. This is a very big topic, rederiving the Born rule, and all sorts of questions come out of there. And I want to present a specific approach to this. And so this is one example of this comes from Wojciech Surek and his original article on decoherence theory. This is taken from the updated version, which he put up a good 10 years later. You can see the reference down here. A pointer as to the state of where this divide between quantum and classical, or the divide between the reversible part, which is on the quantum side, and the less reversible part, which is on the classical side, where this comes about. And you can see here, this is very often thought of as a question of the Hilbert space dimension, in essence. Yeah. So once something becomes macroscopic, somehow we need to use the irreversible laws of physics. And of course, this is something that has occupied, as we've said, this goes back to Niels Bohr, as mentioned here, the Heisenberg cut. So Werner Heisenberg would have thought about this. The Heisenberg cut is somewhere along here. That's where you decide to apply the classical part to what describes your measurement apparatus, etc. Yeah, and so the question that you want to answer is, can we do with the reversible dynamics to model measurement? And then what gets measured? Yeah, that's another question that comes out of this, as in what basis gets measured, yeah, on the side of the system. And let me refer back to a comment that was made yesterday of the quantum measurement problem being a theorist's problem. Yeah, some might even say, is this not a philosopher's problem? I want to, a little bit, something we have in mind here is actually to go the other way around and encourage even into the real experimental side, thinking about proposing and doing experiments that resolve this boundary a little bit better. And that's a tough task. That's not something to ask of experimentalists as such, but that's the ambition to think about here. And Kevin is shaking his head there. You can comment on this later. I'd be curious. But good. So a point here to make at the Quantum Energy Conference is a thermodynamic point, which has also been made a few times, that people say quantum measurement is in conflict with all three laws of thermodynamics. I've left the second law out here. But for the first law, you can notice that probabilistically, when you measure a state that's in a superposition of energy eigenstates, you get something out that seems to have a different energy from what you had before. If you consider this a problem or not is up to you, because of course on average energy is conserved, but if you make a specific measurement, you get a specific outcome in a specific branch of the world. Yeah, and then maybe a bigger problem, or a more fundamental problem, is the third law and the unattainability principle, that measurement also in its textbook version seems to be in conflict with this. We get a pure state out of something that's not pure initially. This happens even in a classical sense if this is just a diagonal mixture. And we can afterwards reset whatever pure state comes out to the ground state effectively, and that would allow us to cool in finite time to 0 temperature. Yeah. So one way to approach this entire thing is to take a step back and take a more nuanced way, a nuanced picture, a nuanced view on how we think about measurement. And this goes under the term of objectivity. Maybe intersubjectivity would be a slightly more precise way of phrasing this. And how this is said is, I'm taking here a quote from this top reference here. A state of the system S exists objectively if many observers can find out the state of S independently and without perturbing it. Yeah? So this does away with the single measurement apparatus which you would originally have in many approaches to this question, and replace the single apparatus by a more fine-grained notion of the environment, where now an agreement has to occur between the many observers. And this has given rise to something called quantum Darwinism. That's not named after a town in the Northern Territories, but after Charles Darwin, because it's meant to represent the survival of the fittest in terms of the fittest basis that gets propagated during a measurement. And this is a statement about the types of state that would represent an objective structure. Yeah? And let me explain this here. So what you can see here, this is taken from an article by Wojciech Zurek, who is the original proponent of this. The way to think about this is, again, to think about a system that's surrounded by a bunch of environments, which can be grouped together or not. So this could be a qubit and a bunch of qubits surrounding it, and we could group individual qubits together. And what you would want in quantum Darwinism is that as you measure a fraction of the environment, so something between 0% and 100% of the environmental parts, that very quickly the mutual information that you have between the system and the environment goes to the entropy of the system. So very quickly the information contained in the entire thing equals the information of the system, and then as you make it larger, it doesn't really change for a long time. So the extra, that's how this is interpreted, the extra bits of the environment don't really add anything. Yeah? There's some operational sort of challenges that this brings up if this actually represents the right thing, but this is one original viewpoint on objectivity, yeah, quantum Darwinism. There's a second, more recent way of thinking about this, which looks more precisely at the state structure, and this is something called spectrum broadcast structure. Yeah, so it says that we would want, out of these many environments representing the outcome of a measurement, in a sense, we would want a structure like this, where the probabilities of measuring some state J on the system are encoded in environmental states, which should ideally have zero fidelity among different outcomes, that the states representing different outcomes in these environments. And you can see directly that SBS implies objectivity in the sense that we had it before. It also implies quantum Darwinism. There's a slightly more precise way of relating them. The inverse doesn't hold, but if we require an additional independence requirement, we can actually make these equivalent. But so for all practical purposes, what I want to use now are these SBS states. And the reason is that they're a good representation of objectivity. Yeah? And the question that really comes about here is how do we get to these states, right? So all of these statements, quantum Darwinism and the spectrum broadcast structure, they say something about what represents in a sensible way the outcome of a measurement. What is something that where the many observers would agree on what has been measured. The question is, how do we get there? Yeah. And what we're proposing here is specifically that we get there by equilibration. So this is to say measurement is an entropy increasing transition towards an equilibrium state. Yeah? This has the advantage that there's no active control or anything like this involved. Measurement doesn't have a third party switching something on and off at desired times, etc., and that it recognizes a sense of stability. Yeah? And let me explain this a little bit. So there has been a lot of work in quantum thermodynamics over the last 10, 15 years or so on closed system equilibration, where the closed system part is what often throws people off. So let me say this from the beginning. We're thinking of having a pure state in a large system evolving unitarily. So how does equilibration come around in this case? Yeah. So what you would look at is the time-evolved state and averaged over time. Yeah. So this is what I call here rho infinity. In principle, this time goes to infinity. What you have as an intuition is that infinity might be quite short for this to already be pretty close. But to make this precise is an ongoing research program. How large do you have to make t here to get close to the equilibrium state? And then there are certain fairly strong results on the equilibration of observables in this picture. There's one is stated here. So this compares the time-dependent state and how it differs from the time average state as a function of the norm of the observable that's being measured and the effective dimension, which is also called inverse participation ratio. It's defined like over here. And likewise, for the equilibration of subsystems, we can bound the trace distance as a function of one of the dimensions of one of the subsystems, and again, the inverse participation ratio, right? So this gives us very strong results, essentially, on what happens in a closed system that a notion of equilibration can still come around, yeah? The question is now, can we get SBS out of this, yeah? Before that, let me just comment on two things that come up a lot in response to this. So the first part is equilibration is a strictly larger thing than thermalization. We're not hoping to get objectivity or measurement or any such thing out of thermalization because that's a many-to-one mapping. This is the opposite of a measurement. And that's also not what people describe with this equilibration more generally. And the other part is what I've already mentioned, that the evolution remains unitary. So the way to read this is that for almost all times, the system looks as if it were in the equilibrated state. But this doesn't mean that there aren't Poincare recurrences and such things. You're just not worried about them because they're very quick peaks. Very briefly, the system might do something different. And that's essentially the trick for getting something as an equilibrium out that looks like measurement without having to have a control in it. And so the first result that we get in this is that can we equilibrate to this such that the equilibrium state represents SBS? You can convince yourself by noticing that what this equilibration does, it's a pinching map where these are projectors onto the energy eigenbases, these pi up here, that you will require a Hamiltonian of this form if you're hoping to get to an SBS state, where I've lumped all of the environments now for simplification back into a single environment system, because we can actually prove that even in the single environment case, we cannot equilibrate exactly. That's not super surprising, but it's something to notice. So we cannot have exactly an SBS state coming out of this, or in fact, a classical quantum state, which is a slightly more general category of a state. We're more interested, we're not worried about doing this precisely and exactly. We want to do it. We're happy if this can happen approximately. And this is essentially the main result then. So we get this class of Hamiltonians where now these are fine-grained again over these acting on all of the different environments. And we want to get this state out. What we can do is we can start to coarse-grain the environments by grouping them together. And we then approach a coarse-grained state. So you can think of each of these representing a qubit, for instance. And what you get is this fidelity requirement that we had being upper bounded by the exponential of some constant, which depends on the original state, and then the magnitude, the Hilbert space dimension of one of these environments. Yeah? And so this is neat. This basically says we can equilibrate to SBS in principle using these Hamiltonians. This is an in principle result for now. We can get there at the cost of macroscopicity. So as soon as the observers become a little bit larger, we can get there as closely as we want. Yeah? That's the main result. Let me summarize. So closed system equilibration in principle can give rise to something like quantum measurement, or the more nuanced version, which is objectivity. This remains to be extended to more general Hamiltonians, which are not a central coupling to all environments. There's no exact equilibration. We're not really worried about this because we can approximately equilibrate to arbitrary levels of approximation as the environments become macroscopic. So with that, I'll point you to the reference down up here and thank my collaborators and make a quick advertisement for a conference that we're planning, which follows on this theme in Oxford, where you can find further details down, in Dublin, apologies, where you can find further details down here. Thank you.
All right, thank you very much. One question, I think this hand went up first.
I'd like to ask if there's any connection between many-body localization and the equilibration that you talked about. If many-body localization is correct, there can be a system that's macroscopic, and it has many-body local integrals of motion which do not evolve. So the Hilbert state looks like a glass. So this precludes thermalization in large systems. You said equilibration is bigger than thermalization. So the question is whether many-body localized system equilibrates as much as it does not thermalize.
Yeah, that's a very good question. So normally people would distinguish basically 3 timescales in this. The first one is the initial system getting correlated with whatever sits around it. And then there's a timescale of pre-thermalization, which is similar to this equilibration. And on the very long run, something thermalizes. So MBL can sit here in between, because it doesn't thermalize if it exists. Many-body localization prevents thermalization. So I think this would be something to explore if that can fit into there directly. Yeah, thanks.
Thank you very much, Felix, again, for your great talk.